Good morning, class, and welcome to this lesson on fluids number 9, Bernoulli's principle number 2. Today we will be able to know the equation for Bernoulli's principle and be able to apply that equation to some common types of problems. So, in our last video we discussed the idea of Bernoulli's principle. We were just taking the principle and we were applying it to some situations and saying, okay, this is high pressure, this is low pressure, so there's going to be force pushing it this way. Now we're actually going to have an equation to apply to these situations and be able to actually solve mathematically Bernoulli's principle. So first off, I just wanted to point out these are two figures in your book. And they really just demonstrate the idea of Bernoulli's principle. In this situation, we have a horizontal pipe, and this side has a larger area than this side. And so as it flows to the right, this side is going to be moving faster, and so there's going to be less pressure than this side. As you can see, the little pressure gauge right here, this one has less pressure than this side. Pressure also depends upon height, and so in Bernoulli's equation, we haven't gone over any of this conceptually, but in the equation, we are going to account for height as well. So this one has a lower pressure than this one, and so we can take that into consideration in the equation as well. And then we can also have a situation like this, where this has a bigger area and it's lower. This one has a smaller area and it's higher. So it's going to be traveling faster, causing less pressure, and it's also higher, causing less pressure. So these are the very good diagrams to illustrate. Look at, if it's at a higher elevation, it's going to have less pressure. If it's at a wider area, it's going to have more pressure. So let's look at what Bernoulli's equation is. Bernoulli's equation is going to look a lot like the work-energy theorem. We're going to have pressure at point 1 plus 1/2 rho V1 squared plus rho Gy1 equals pressure at point 2 plus 1/2 rho V2 squared plus rho Gy2. In case you're wondering where this equation comes from, I'm not going to derive it right now because that's a whole video in itself. I highly recommend, if you want to know the derivation, just type in true physics into YouTube, and you're looking for fluids. Number 21. She does a very good job of deriving this equation and showing you how to do that. This does get derived from the work-energy theorem, which is why it looks a lot like the work-energy theorem. As you notice, this kind of looks like kinetic energy, and this kind of looks like potential energy on both sides. And so it's very similar in that nature. So as you can see here, we have accounted for height, y1 and y2, and we've accounted for speed, and we've accounted for the different outside pressures. So let's look at some common situations that we can use to apply this equation. Let's go back to our airplane wing. So we're going back to our airplane wing. We have an airplane wing, and we have these streamlines of air going around the wing. And let's call under the wing P1, and let's call above the wing P2. Okay? So P1 and P2 are like P1 and P2 in the equation right here. Okay? P1 and P2 are like the equation right here. So with this airplane wing, if I know P1, and if I know the velocity under the wing and above the wing, I can add that in. So 1/2 rho V1 squared plus rho Gy1 equals P2 plus 1/2 rho V2 squared plus rho Gy2. Now, here's something I want to point out. Is there a height difference between P1 and P2? There is. But the height difference is so small, we can cancel it out. I mean, typically we're talking about height differences and pressure. We're talking about huge water towers, or we're talking about things that are very, very large and fluids are flowing very far down, like at a dam or something. So in this situation, this is a very, very minor change in height. Okay? The pressure is not going to be very much different due to height. It's almost like saying, is the pressure at my head different than the pressure at my feet? Well, yes, because at my feet it is lower down, but we're talking very, very minor differences. So because this change in height is so small, this change in height is very, very small, we can just assume it's 0. Okay, so this cancels out right away. Okay, so now the equation already gets very simple. So let's say we're trying to solve for force. What is the force on the wing? Well, to know the force on the wing, we must know the pressure difference. We must know the pressure difference. So if I want to know the pressure difference, what I'm going to do is I'm going to subtract P2 from both sides, and now I'm going to have P1 minus P2, and I'm going to move this one to the other side as well, equals 1/2 rho V1 squared, V2 squared minus 1/2 rho V1 squared. And so P1 minus P2 equals 1/2 rho, because I can factor that out, V2 squared minus V1 squared. So if I'm given both speeds, and I know the density of air, because that's the fluid we're talking about is air, I can calculate the pressure difference. And if I know the pressure difference, pressure is just force over area, and more than likely, they're going to give me the area of the wing in the picture, in the problem, and I can solve for force using that. So this is a common example of we have two pressures. We were able to cancel out height because it was negligible. It didn't really matter. We found the pressure difference. Notice I just moved P2 over to this side. And then we were able to calculate because we know the speeds of the air above and below the wing. So that's one very common type of problem. Let's look at another type of problem. Going back to our house situation. A very common type of question is asking, what is going to be the pressure difference, or what is going to be the force on a window? Because outside the house, I have very, very strong winds going around the house, okay? So these very, very strong winds are going around the house. What's going to be the pressure difference on the window? Well, I know that the force on the window right here, is going to be pushing outward. The force is going to be moving outward because the inside of the house the air has no speed, higher pressure. On the outside of the house, it has a higher speed, less pressure. So once again, I want to write my equation down, P1 plus 1/2 rho V1 squared plus rho GY1 equals P2 plus 1/2 rho V2 squared plus rho GY2. So notice here, I'm going to call this pressure 1 and this pressure 2. Okay, so P1 and P2. These are two different pressures. If you notice in this problem, it's going to be the same as the last problem. There is no change in height from the inside of the house to the outside of the house. So this change in height just goes away. Okay? And the cool thing about this problem is if we're talking about the inside of a house, the air has no speed inside of a house. So inside of the house, the speed is 0. So now our equation simplifies into P1 equals P2 plus 1/2 rho V2 squared. And if I'm trying to find the force on the window, just like last time, I would find the pressure difference between the two. And knowing the pressure difference, I would then plug in force over area, assuming that I know the area of the window given in the problem. So this is another example of Bernoulli's principle. Let's do one more example to finish off. Let's look at a water tower. Okay, so we're assuming we have a very, very large water tower, and this is going to be funneling down into some sort of spigot, into a sink, into a hose, into something else at our home. Okay, so let's write our equation. P1 plus 1/2 rho V1 squared plus rho GY1 equals P2 plus 1/2 rho V2 squared plus rho GY2. Okay, well, in this situation, there's going to be a change in height. So we cannot cancel these out. This is definitely going to be important to us. And this question is more than likely going to ask, what is the speed at point 2? So I'm going to call this point 1 up here. We have water up here, and this is going to be point 2 down here. What's the speed coming down here? So The one thing I can cancel out is this. So, because this is a very, very large area, we can remember the equation of continuity. Okay, A2, V2. This is so much larger than the area of the spigot down here that you could imagine that this water is going to drop very, very, very slowly. I mean, water is going to be pouring out here and pouring out here, and this is going to move, centimeters per hour or something like that. So the reality is, because this is going to be dropping so slowly, the velocity at point 1 is pretty much 0. Okay, it's not exactly 0, but it is pretty much 0. So we can cancel that out right away. So that's kind of nice. Okay, the pressure on the top here is going to be equal to atmospheric pressure. The air is pushing it down. And the pressure pushing against the water this way, so we have pressure on this side and pressure on this side. So the pressure on both sides is going to be atmospheric pressure. So atmospheric pressure plus rho g y1 equals atmospheric pressure plus 1/2 rho v2 squared plus rho g y2. So notice this. There's atmospheric pressure pushing from the top, there's atmospheric pressure pushing from the bottom. Because these two pressures are the same, they cancel out. So now we have rho g y1 equals 1/2 rho v2 squared plus rho g y2. So let's assume now that, let's say this is 10 meters tall. Well, if this is 10 meters up here, then down here it's 0 meters. So the height at 2 is going to be 0 as well. So our equation simplifies from this big old thing up here to rho g y1 equals 1/2 rho v2 squared. And then if we want to solve for v2, we would cancel out rho, and then it would just be the square root of 2gy equals v2. Notice this looks exactly like our conservation of energy equation, where we have an object sitting up here, and the potential energy up here is mgh, and the kinetic energy down here is 1/2 mv squared. It's almost exactly the same. Now, if you did this on like the AP test, you would not get credit for this. You have to show you're using Bernoulli's equation, but notice how similar it is. The height up here of the fluid is going to translate into velocity down here. It's like having potential energy and kinetic energy. So you should notice some strong similarities there. So we covered 3 situations. We covered a height situation, we covered a house situation, and we covered a basic airplane wing. And the purpose of this video really was to get you to see, here's our equation right here, and here are some common ways to manipulate the equation to cancel stuff out to solve what you need to solve for.